Hello and welcome to our educational video on the Fluidic Telescope (FLUTE) project, a joint venture between NASA and Technion Israel Institute of Technology. In this video, we'll explore the FLUTE project and how it envisions a way to make huge circular self-healing mirrors in orbit to further the field of astronomy. As you may know, larger telescopes collect more light and allow astronomers to peer farther into space and see distant objects in greater detail. These next-generation large space observatories, envisioned by the FLUTE project, would study the highest priority astrophysics targets, including first-generation stars, the first to shine and flame out after the Big Bang, early galaxies, and Earth-like exoplanets. These observatories could help address one of humanity's most important science questions: are we alone in the universe? Currently, payloads launching to space need to stay within allowable size and weight limits to fly. The state-of-the-art 21-foot, 6.5-meter aperture James Webb Space Telescope needed to be folded up origami-style, including the mirror itself, to fit inside the rocket for its ride to space. The aperture of an optical space observatory refers to the size of the telescope's primary mirror, the surface that collects and focuses incoming light. The aperture for the space observatory envisioned by FLUTE researchers under the current concept would be approximately 164 feet, 50 meters, in diameter, half as long as a football field. However, conventional technology for making optical components for telescopes is literally a grind. It involves an iterative process of sanding and polishing solid materials, such as glass or metal, to shape the precise curved surfaces of lenses and mirrors needed. Using current technologies, scaling up space telescopes to apertures larger than approximately 33 feet, 10 meters, in diameter does not appear economically viable. FLUTE's novel cost-effective technology approach, in contrast, takes advantage of the way fluids naturally behave in microgravity. All liquids have an elastic-like force that holds them together at their surface, called surface tension. This force is what allows some insects to glide across water without sinking and gives water droplets their shape. On Earth, when droplets of water are small enough, 0.08 inches, 2 millimeters, or smaller, surface tension overcomes gravity, and they remain perfectly spherical, much like droplets of morning dew beating into tiny spheres on plant leaves. If a droplet grows much larger, it gets squished under its weight. But in space, where fluids are free-floating, unhindered by gravity, even large amounts of liquids assume the most energy-efficient shape possible, a perfect sphere. Liquids can cling to surfaces due to a physical property called adhesion. In microgravity, if a sufficient amount of liquid is made to adhere to the interior surface of a circular, ring-like frame, the liquid will stretch across the inside of the frame and naturally form a curved shape, called a spherical section, thanks to surface tension. By using the right volume of liquid, it is possible to make the surface of the liquid curve inward instead of bulging outward. If the liquid is reflective, that inwardly curved surface can serve as a telescope mirror. FLUTE would launch liquids to space as the raw material to make optical components in orbit. The primary mirror would form within a huge circular frame and remain in a liquid state with an extremely smooth surface for collecting light. FLUTE's technology approach is theoretically able to scale up to very large sizes. The technology could potentially enable telescopes with apertures measuring 10 times, or even 100 times, larger than telescopes to date. A unique feature of the liquid mirror would be its ability to self-repair if damaged in space. For instance, if a micrometeor impacts the mirror's surface, it would naturally heal itself within a short period of time. Thank you for watching. Please like and subscribe for more interesting topics like this.